hello. Yeah. All right, find your seats, grab a drink. We're just about to start. I'll turn off the music. Then we'll go kind of downstairs, or?
I mean, I can wait.
Yeah, you can also keep an eye on when they check in, and you can see this down. Yeah. I love it that people are taking front row seats. All right, welcome everyone. My name is Sif. I'm running the community here at Merantix AI Campus. Who is here for the first time? Cool. No, you're not here for the first time. Yeah, so very welcome. We are kicking off this series, AI4Science. We've done it once before, but then we went a bit silent, and now we have joined forces together with Trip Systems, Dunia, and CUSP, and we're going to be running these series regularly. Super interesting topic and a lot to cover. I already want to announce the next one, which is going to be on the May 18th, AI4Science Hackathon. So mark your calendar. We're going to announce everything, announce things soon. Yes, so I want to quickly just tell you what we do here at Merantix. So we are a collaboration hub of AI companies. We have 60 teams sitting here on campus, everybody working in the field of AI. We run a tight content calendar, so keep an eye out on our website. We have a lot going on. And I want to do two plugs. One, we are kicking off our third edition of the Hacker Room, which is a residency, community residency here on campus of people that want to build, hack, are really thinking about building something, don't know what they might have in mind already, or already have an idea and want to come and work from campus for 4 months and yeah, connect with other technical people, engineers, spare, and so on. We have applications live, so you can see on our tables here a QR code, or come talk to me afterwards. And then we have a new entrepreneur in residence. He's here in the audience somewhere. And his name is Pratap, and he's working on wet lab automation, so AI for CROs. There he is. If anybody's interested in that topic, go find him after the talk. I will now give it to Nasim, who is one of our collaboration partners, and he will introduce the speaker this evening.
Awesome. Thanks, Seth. Yeah, hey, everybody. Love the numbers. Welcome. And also a special welcome to the folks tuning in from Mila in Montreal. We're live streaming the event there as well. I'm Nasim. I'm a co-organizer of this event and a co-founder of Tipri Systems. And I'm super stoked to, welcome you all to this edition of AI4Science with Annalena. And okay, so before we get started, I'd just like to tell you a little bit about what is this about? What are we doing here tonight? As we're entering this age of abundant intelligence, right, where you have these alien minds in a certain sense, right? They don't think like we do. They don't work like we do, but like ours do. But you feed them GPUs and electricity, and they the tokens keep coming. But as it turns out, you can actually, deploy those minds to the service of discovery and science, right? And that changes some of the assumptions that we've been making about, how we do science, what the scientific method is, and what the future of the scientific method is. And many of those assumptions would need to get reimagined even. This talk series is like a dialogue with the people at the forefront of that endeavor, right? And yeah, so tonight is a perfect example of, you know, like what I mean by this, right? And for gravitational waves, but like it's also about black holes. Black holes are perhaps like some of the craziest things that are out there in the universe, and they challenge, you know, like what we understand about our reality, our world, right? And so it's not a surprise that people are really trying to figure out how they work. You know, like how do, you know, like what's the physics? How do these things, you know, like interact, and how do they collide? And you know, like understanding this will teach us a thing or two about about the nature of our reality itself, perhaps. And Annalena's work is all about accelerating that process, right? And which I think is like very cool. And she's a PhD candidate at the MPI for intelligent systems with Bernhard Schölkopf, and co-supervised by Alessandra Buonanno at the Max Planck Institute for Gravitational Physics, or like the Albert Einstein Institute. So, you know, like she's right there at the intersection of AI and gravitational waves. So the perfect person for this. Yeah, she is a part of the Ellis PhD program. And just last month, she was selected to join the Lindau Nobel Laureate meeting. So congratulations, that's awesome. So, you know, without further ado, I'll hand it over to Annalena for her talk.
Thank you so much, Nassim, for the great introduction and also for the invitation for me to come here and give this very exciting talk to you all. So let's get into it a little bit. So now you've heard a lot about me, but I want to know more about you. So first of all, like, what's your background? Who's here who has some machine learning background, who would say, oh, I have some machine learning experience? Is there someone from maths? Yes. Someone from physics, that will be interesting for me. Oh, okay, wow, quite a few people. And I hope, like, if you have this Windows logo as your background, I hope, like, sorry for you. I hope you can update it. Okay, great. So there will be some memes in my talk, as you just saw. Nassim asked me to include some memes. Let's hope they fly. I want to make a disclaimer at the beginning of my talk, because you're all here because, yoo-hoo, gravitational waves sounds so cool, and we're even combining it with AI, so two really exciting topics. But I have to tell you that there's nothing new on the machine learning side that's going to happen in this talk. So this might be a little bit disappointing, but it will give you an idea of that the newest machine learning developments might need some time to actually be put into practice, into a running production system that we can trust as physicists. But of course, in my talk, we will have black holes, so it will be very exciting on this side. So in the night, when you go outside, you look at the sky, and you can see a lot of stars, you can see the moon, galaxies, very exciting things. But in between, there's a lot of black, and a lot of stuff that we cannot see. For example, black holes. So the question arises, how can we actually observe something which is black, which is like refuses to be observed in any possible way? And we do that by looking at gravitational waves. And gravitational waves are predicted by Einstein's theory of general relativity. And you can see here two black holes. They attract each other because of the gravitational force. And what is happening if they meet, they're in spiral. You can see this here in this simulation, and then they merge into one big black hole. And this is called a gravitational wave. This is called a black hole merger. And in the process, you can see here in green that the distortion of the space-time is so strong in this merger process that it sends out a gravitational wave. So you can see here how it gets stronger and stronger while they're in spiral. And now you can see the peak of the gravitational wave moving outwards through the universe. And then the two black holes relax to one bigger black hole. And what happens then is that at one point, these gravitational waves arrive on Earth. And since they are ripples in space-time, what is happening is these gravitational waves distort the space. This is here like vastly exaggerated, but it gives you an idea that they actually move through Earth, they can move through matter, and distort the space that we live in. And this is the phenomenon that we now use to actually observe these gravitational waves. And Einstein didn't think that this would be possible. So by observing the first gravitational wave in 2015, we actually proved Einstein wrong, because we can now measure changes in a distance that are so small that even Einstein didn't think it would be possible to do that. So how do we actually now measure a gravitational wave? We use lasers. Lasers can be very precise and measure distances very precisely. What we do is we build an interferometer. This works like this. You might have seen this in a physics class. So you use a laser beam pointed at a half reflective mirror, and you get one beam going upwards, one beam going to the right. They get reflected at the test masses at the end, and then they recombine here in this mirror and move onwards to a detector. And since you have two separate laser beams, the light waves will interfere, and you will observe an interference pattern. This is not exactly how this would look like in the gravitational wave detector, but it gives you an idea. Now we can measure these distances very precisely, and if the distance of one of the arms changes, this will change the interference pattern. So if now a gravitational wave comes and moves through our interferometer, this will distort the distance. It will change the distance in one of the two arms, and this will then change the interference pattern. And this is how we actually observe that a gravitational wave is moving through our detector. So now we don't only use one single detector, but we use two detectors, or even more than two, ideally 3 detectors, because we have a lot of noise, and these detectors are very sensitive. So if there's an earthquake happening or a plane flying over the detector, you will see this in the detector because it has to be so sensitive. So here now I will show you how the first gravitational wave merger looked like. On the left, you can see the 2 black holes in spiraling. On the right, you can see in gray the signal and how it is quite noisy. And in color, I plot the simulation which best fits the signal. And you can see you have an in-spiral period, and then at the peak here, the 2 black holes merge, and then they relax back to a ground state. And this is the type of data that we're dealing with. So now we have this data, so how can we now go from data back to the underlying physics? Because this is what we're actually interested in. If we observe the data, we don't know anything about the 2 black holes, and this is what we actually want to know, right? So we have the 2 black holes which merge, and this system is described by 15 physics parameters. Some of them are very obvious, like the 2 masses of the black holes. For example, they also have an additional spin component. Some of them are less obvious, maybe the sky position. So where from the sky did the signal come from, or the distance, how far into the universe did this actually happen? Then the universe helps us by kind of facilitating the black hole merger, and it emits a gravitational wave which arrives on Earth and is measured in one of these detectors, which are currently online, Hanford and Livingston in the US, and Virgo is based in Italy. And then we get an observation like this on the right. And now what we want to do is we want to do the inverse process. We want to go back from the data to the underlying physics parameters, and for this we do posterior estimation. And this means that we are not interested in a point estimate. We want to actually have the full posterior distribution. So we want to not only have uncertainties over each parameter, but we also want to have the correlations between individual parameters. This is very important because the mass, oftentimes multiple different simulations can fit an underlying signal. And also some parameters like the sky position, you need 2 parameters to describe it. So these 2 parameters will be highly correlated. So now you have like a general overview, like what are gravitational waves, how do we detect them, what are we interested in? Before I go into the details about how we use machine learning, let's first explain why is it exciting. And for the whole time of humanity so far, we were always able to look into the universe, to observe light sources like stars or galaxies. So this is what we have been used to for the whole of science so far. But in addition to seeing, we can also now hear basically the space-time by actually looking at gravitational waves. This is a kind of a new window into the universe, and we can now jointly observe basically systems, so black holes merging or lighter black holes called neutron stars merging. And in addition to basically observing the gravitational wave, we can also observe electromagnetic follow-up, so light. So we have light in addition with gravitational waves. We now know that black holes exist, which we were not 100% sure before, because so far it was only possible to observe them in an indirect way. So at the center of a galaxy, there was something very massive, probably a black hole. But now we know there's no other possibility. There are even more black holes observed than we have expected from theory, and the black holes are more massive than we ever thought possible. And it's unclear how they actually get that way. We can also now test whether Einstein's theory of general relativity is wrong, or whether there's some additional terms, or whether the universe actually does something more than what Einstein thought about. We also know that for where some elements come from, like gold or uranium, these are like very heavy elements, and they are produced in binary neutron star collision. So if you have a star which dies, it can form a black hole if it is above a certain mass threshold. If it's below that, it will kind of shed some outer layers and collapse into a neutron star. These are super dense. We don't know what's going on inside them from a physics perspective, but of course they are heavy enough to generate a gravitational wave when they merge. And in 2017, it was possible to observe two neutron stars merging, which led to multiple Nature and Science papers, because we observed not only the gravitational wave, but also pointed some light-based detectors in this direction and actually observed the light that also came from this collision, because these two neutron stars were not heavy enough to capture the light. And now from this, we learned that gold and uranium and other elements are actually produced in these collisions. And the last thing I want to mention is that we can actually observe and measure how much the universe expands. And this is an ongoing discussion in physics. So the cosmic microwave background gives you one prediction or one value for how much the universe expands, but you can look at supernovae type 1a stars, which tell you a completely different values, and they don't agree with each other. So it's kind of a physics war going on there. And gravitational waves now give you a different opinion about this. We're not there yet to actually constrain the parameter well enough, but we will be there with more and more detections. So now the question is, why do we need machine learning for gravitational wave science? And at the moment, we currently observe like around 5 events per week when the detector is switched on. You can see in 2015, when we started observing, there was like a handful of detections. With every observing run, the detector is improved significantly, so we actually suppress more and more noise, which means we get more and more detections of gravitational waves. And with every observing run, the number of detections improved drastically. So now we are at around 5 per week, but in the future, with even better detectors, we will measure around 200 per day. And the standard methods, if you want to do parameter estimation for a single event, this can take hours to actually weeks if your simulator is very expensive for a single black hole merger. And this is very expensive. And this will not be possible to be done with 200 detections per day. So we need machine learning to speed this up significantly to just handle this massive amount of data that we will be getting in 5 or 10 years. And what we use as a technique is called posterior estimation, which is a simulation-based inference technique, and I will explain how this works. So what we use here is that we have very good simulators. In physics, a lot of people build simulators, and we actually rely on physicists from the gravitational wave side to build these simulators based off of Einstein's theory of general relativity. And because the theory is so good, we can actually simulate these gravitational waves very well. And what we now do is we say, okay, for example, for the mass, we have some range which makes physically sense. So we have a prior distribution, and we can draw samples from it. So let's say we draw a sample, the mass is 50 solar masses. And then we put this into our simulator, which then converts this initial mass value into the shape of the gravitational waves. So it gives us simulated data. And we can then use this bunch of simulated data to then train a density estimator. Which now, where we minimize the log likelihood. And with this density estimator, once it's trained, we can then evaluate it on real data. So on data where we don't know the underlying parameters, so we don't know what the mass is. But we can now use our trained model, input the data that we have observed, and then obtain a posterior distribution over the mass. And this is how we get basically the inverse direction going from the data to the parameters. Yes. Yes, maybe you need a microphone. You can take mine.
So you said you're working in the 15-dimensional parameter space, and your simulations are really expensive.
Yes, yeah, it works.
Yeah.
Yes.
So you 15-dimensional parameter space, really expensive simulations?
Depends what simulation you use. So there are some simulations which are very expensive and some simulations which are quite fast. So you can parallelize this with a bunch of CPUs and you might get maybe 10 million samples in a day or something.
Okay, because that was my question. How do you make sure that your simulation data covers the full parameter space? How do you get enough simulation data?
Yeah, so you have to use enough simulations. And there's kind of a hierarchical chain to having some simpler simulators, which have phenomenological models, or their approximations of how the gravitational wave looks like. And they are, as I said, quite fast. And then there are more expensive models. And at the far end, they're like numerical relativity simulations, which actually place a fine grid over this whole space where the two black holes are moving. And then this takes basically a week to run on a supercomputer. And to this date, we have around 1,000 of these simulations. So you cannot train a machine learning model on this very expensive data, but we can train it on kind of the ones which are actually like regularly used in the official analyses. Yeah. Thank you for the question. Yeah, I think I forgot to say that. If you have any questions during the talk, I'm very happy to take them right away. Thank you. Of course. Yeah, Kagra is the one in the pen. Yeah. So ideally, we always have 3 detectors online and running at the same time. And the reason is that we want the sky position to be very precise. And because of triangulation, similar to how GPS works, you need at least 3 satellites for GPS, but 3 detectors for gravitational waves. So there are 2 in the US and the one in Italy. And in the current observing runs, you always have the 3 detectors online. So I know one, there was only 2, like only the US based, but now we have 3. And Kagra has started operating, but they are in a kind of a preliminary stage. So they currently try to push down their noise levels further. So they are kind of in engineering runs. And the next observation run will start in October for 6 months. And there we will definitely have 3 detectors online. So the 2 LIGO detectors and Virgo, and Kagra might join towards the end of the 6 months. But like having an additional detector, a 4th one, is not so much more important because if 3 are online, that's perfect. But of course, all detectors have downtimes. So it can happen that during an observation, one detector needs some urgent maintenance, and then you just have 2. So if you have 4, then you at least have a backup option. Yeah, cool. Great. Thank you so much. So now let's get into how we take this framework called posterior estimation and apply it to gravitational waves. And we have built a package called DINGO, so Deep Inference for Gravitational Wave Observations, where we basically implement this framework and apply it to gravitational wave data, because you need a lot of specific pre-processing to actually do that. So as I said before, we need a simulator. So we have very good ones. So we sample from the prior, put our parameters into a simulator, and then we get these pairs of parameters and data. And on the right, you can see a waveform. I want to just comment that now the x-axis is the frequency domain, not the time. So we apply a Fourier transform to it. It's basically the same signal. It's just a little bit easier for us to process this data. And now what we do is we, of course, have to add noise to this, because this is a deterministic simulation and it's not how we observe it in a detector. And the noise curve of the detector looks like this. And this is basically measured when there's no signal present in the detector. And you can see that at specific frequency ranges, the detector is less sensitive and others it's more sensitive. And it has these spectral lines. For example, if there's like the grid frequencies of the electric grid, you will see a spike at around 50 hertz. And this is something which will, of course, we need to include in our data to make it realistic. So what we do is we take this noise curve and we assume that our noise is stationary and Gaussian, so it doesn't do any weird things. And then what we do is we plug this curve into as the standard deviation into the Gaussian formula and sample from this. So we sample some noise realization, and then we add this on top of our simulation. And this is now how actually real observed data would look like, but from the simulator, we only get basically the clean waveform without the noise effect. And this is what we can put now into a density estimate and what we can use for training. If you work on real data and sensors, you know that these noise levels, they are not stable. So they will change over time. So if you switch the detector on and 6 months later you look again, the noise curve can shift. And we have to account for this. And what we do is we basically collect create a whole collection of these noise curves over the whole observing run, and then we sample from them. So in addition to sampling and noise realization, we also select one of these noise curves and then again add them to the simulation. And now finally, we have prepared our data, we can now train the model. So we do not only put the data into our machine learning model, but also the noise curve. Because as I said, the noise curve can shift over time, so it's good to tell the model about what's the current state of the data. And if we then at the end evaluate on real observations, what we would do is we have a stretch where the signal is in, and we also take a stretch before the signal, which we then can use to estimate what the noise curve is at this moment, like right before the signal came into the detector. And we put this now into an embedding network. So the reason for this is that the data is high dimensional. So here we are talking about the data D and Sn, both of them can be between 3,000 to 10,000, 100,000, or even multiple millions of data points, depending on what type of signal you're looking at. And of course, you cannot put this into a density estimator, so you have to compress it first. So we use an embedding network that can be a simple residual network to compress it down to around 100 dimensions, and then feed this as a conditioning into some type of density estimator. And this is the point where I'm like, okay, you could use something more fancy than a normalizing flow, but we actually still use normalizing flows, and the simple reason is that they are very fast. And there's no, like, of course you can do flow matching as an example, but there you then need to integrate an ODE, which gives you inference times of minutes instead of seconds. And this is why we still use something which is already 10 years old. Yes, you had a question. Yeah, so in frequency domain, you need a specific resolution. So if you have very long signals, so for example, as I was mentioning, these neutron stars, they can be observed in the detector multiple minutes before they actually merge. And then, of course, in frequency domain, you have 1/t, so you have a very small resolution to actually resolve the signal completely in frequency domain, and this gives you very high dimensional data. There's not so much physics information in it, but you need a way to compress it without losing information, which is quite challenging, because then the posterior estimate should still be correct, right? Yes.
You collect the noise curve at the beginning, but are you saying the noise does also change during like the trajectory of D, correct? Okay.
Yeah, so currently we're kind of running in a specific mode. So how the collaboration, how this works internally is you observe the data in the end, you do one big evaluation of all our events. This means you can collect the noise over the whole observing run and use this for training your model. But of course, if you want to run online, so take the data as it comes in, then you have to in some way be adaptive. And this is something we still have to work on to how to improve this. But you can also generate like more an artificial noise data set. So you take one realization and say, okay, how could this change? And then you can train your model on that. Cool. Okay. So to finish the slide, like normalizing flows, the density estimators are usually trained with negative log likelihood loss. And yeah. So now there's one question that I always get from physics audiences, maybe not from you, but what if my model is wrong? And this is, yeah, it can definitely be wrong. But the point is, for our purpose, for physics discoveries, it is not allowed to be wrong, because potentially, depending on what you observe, you might get a Nobel Prize. So you're not allowed to make any mistakes. At least you have to tell the physics community, we can't trust this result in this case. So what we're doing is we use importance sampling to validate and correct our model. So let's say we have two distributions. P is the true posterior, but we're not perfectly there. So our posterior distribution is the pink one, the Q. And what you can now look at is the ratio of these two distributions, which is called an importance weight. So and the problem now here is that, of course, if Q is equal to P, the ratio will be 1. But if not, then you have some deviation. We cannot compute the ratio directly because the posterior, of course, that's what we want. So this is not accessible. Like if we would have it, we wouldn't do this whole thing. So what we use is we use Bayes' formula to rewrite the posterior as the likelihood times the prior. And the evidence is a constant, so we can discard it here. And this is what we define an importance weight. And the cool thing is that actually the prior is known because that's what we define based on our physics intuition. And the likelihood is, as I explained before, we sample from this Gaussian to generate our noise, right? So we can actually, the likelihood is actually a Gaussian distribution, which we can evaluate. And that's why we can compute this importance weight, which is really cool. And for this example here on the right, you can see that we are overestimating the true distribution. So we have a too high density. So here we would have a low importance weight. And in other regions, we are, for example, underestimating. So any sample in this region should be more important than our normalizing flow has predicted. And with these importance weights, we can rewire our samples towards the true posterior and actually give a kind of a confident result, which is actually correct. The nice thing is that importance sampling also gives us a performance metric, and we call this the sample efficiency. And to give you an intuition of what these values can be, so here in 2 dimensions, let's say we have a Gaussian target distribution, so we want to sample from this Gaussian. But if we have a poor proposal, this is just sampling uniformly. Of course, there will be regions where we're underestimating this Gaussian. Here at the border, we have a low importance weight, and then in some other regions, we're underestimating it, so we have a high importance weight at the peak. And this gives us a low efficiency. If we then go to the right plot, here we have a Gaussian, which is very similar to the target distribution. And you can see that the importance weights, they only go from 0 to 2. They don't go up to 20. So the variance is smaller, which gives us a higher importance weight. Of course, efficiencies of 70%, that's only possible in 2 dimensions, and we are in 15 dimensions. So the efficiency you will see on the slides following, they will go down. Yes, another question. So what we would do, let's maybe explain this here. So we have points here, like let's say we have this uniform distribution, these samples as the proposal. Yep. Mm-hmm. Yeah. Yeah, we reweight the density. So we have Q, and we can compute. Sorry, I can't use my cursor unfortunately, but you know that on the region on the right, for example, the density is higher than it should be. So the importance weight will be low, and which means you can actually reduce or change the density by giving it less importance, which means you actually reduce the density to the correct orange line. So you don't change the samples that you draw, but you change how important each individual sample is. And there might be regions where you have too many samples, so you give all these samples, which are too many, less importance, than in regions where you have less samples and give them more importance, basically, because you have too few samples. Does that help? No, these are samples which are now my posterior distribution. So the physics distribution over the masses, for example, or the distance. Yeah. So here, basically, x and y, these 2 coordinates would be, for example, the mass 1 and mass 2. And you want samples in this space here. Thank you for the question. Okay, so the challenge now is real data is messy. Not only because of the noise, let's say we've handled that, but it changes a lot because, for example, detectors are offline, or there's some noise artifact which is not Gaussian in some frequency range. So on the right, you can see how different events are analyzed. So this is around 50 events from an observing run, but the settings change from each event. So for example, detectors can be offline, or you have kind of artifacts in the frequency range. You want to remove this when you do the evaluation. And with a standard embedding network, like a residual network, you cannot do that. So what we would actually need to do is every time you have a different setting, you would need to retrain your model or train a new model from scratch. And this will become very expensive if you have these 17 different configurations here on the right. So my work was how to make this more flexible. And what we do is we replace this embedding network with a transformer encoder. And we train the transformer encoder then on signals on varying lengths, so different numbers, like detector configurations or different frequency ranges. And by training it in a flexible way, we can then adjust the settings or adjust which tokens are actually active at inference time, and basically have a flexible model which can analyze all these signals I showed you in the slide before with a single model. And this is what we call DINGO T1, so transformer version 1. Probably there will be a version 2 at one point. And for a transformer, one important question is, how do you actually build these token segments? So let's start again from the data here we have on the right. And what we do is we first use a compression technique to handle this high dimensionality in some way. And this is a compression based on physics intuition. And you might remember the signal I showed you before. There was a lot going on at the lower frequency part of the signal, but at higher frequencies, there was not so much in the simulation. So what we do is we subsample the signal by compressing it in a way which is based on this physics intuition. If I zoom in here, so at low frequencies, we start with the resolution, which we had in the beginning. But then at one point, we actually know that we can reduce the resolution because there's not so much information content anymore. So we always average 2 frequency bins, then we average 4 frequency bins, 8 frequency bins, and so on. And this is, you can already see on the right, that this reduces also the noise that we have on top of the signal because we average noise from different bins. And then in the end, we divide it in equal segments to then feed this into a tokenizer. Okay, let's go into the architecture. So now we have these like tokens. We feed them into a tokenizer, which is just a small network, which takes into account which frequency range the signal came from, also which detectors. And we combine this with a token mask because we want to remove some tokens during training, because at inference time, we want to, for example, remove a complete detector. We combine then different tokens from different detectors and with a summary token, where we want the transformer to basically store all the information in, and then feed this through a transformer encoder. I will not go into so much detail here. You can ask me questions, of course. And then in the end, we compress the summary token into around 100 data points and feed this again to the normalizing flow as before. And we train this whole thing end to end. This might be a little bit surprising because there's a lot about pre-training nowadays. The reason is that with these parameters that we have, that we inputted into our simulation, we have labels. Like we are in the fortunate space of actually having labeled data, which is in text not the case, right? And that's why you would do unsupervised pre-training, but in our case, we can do just supervised training from the start and not first basically try to reconstruct a signal. And then, of course, the model might learn other things which we're actually not interested in, because we're mainly interested in getting the parameters. Yes. So the labels, what I was talking about labels is that the parameters, so the masses, these physics parameters, and they are similar, like they're exactly the parameters we're interested in at inference time. So how the simulation worked, we had these labels. Basically, we put them into a simulator, and then we got like a simulated signal. And then on top, we added a noise to make it more realistic. I think that's what you were saying, right? So
does this mean that like those of you want to learn sort of new efficiency, right? Like labels physics get but you're generating labels with like a simulator that's sort of artificially approximated, such as
yes. So of course, there's an assumption about the model that we make. So we train a model based on a simulator. I think that's what you're going towards. And of course, we trust the simulator. We put the trust in the simulator that this actually described the physics. But of course, as you were saying, this might not be completely correct. So what a lot of people do is you train models with 2 different simulators. So you use one simulator and then you use another simulator, which, for example, includes an additional physics effect, which is not included in that simulator. And then you can do model comparison. So you can compare, given this data, what is actually the model where it's more likely to come from. Yeah, that's super interesting. Yeah. And now to train this model, we basically have to do some masking during training. So we kind of use some data-inspired masking strategy to, for example, remove tokens more likely together if they are from the same detector or from a specific frequency range. And then we train this model around like 9 days on 8 GPUs. And then at inference time, we can now, for example, chop our signal at a specific frequency bin. And it could happen that this frequency actually is in the middle of a token. So what we do is we then mask the token completely and then perform importance sampling at the specific frequency value to basically correct for the error we might have included because we removed a complete token. And this gives us an unbiased result. So now the exciting stuff. What can we now do with such a flexible model? The first thing is we can take an event and analyze how does this posterior distribution look like if the signal would have appeared in different detector combinations? So the same event, same signal, but different detectors. So we just remove all tokens from one detector and then evaluate, run inference again. And here you can see one of these posterior distributions. So here we have, for example, one of the masses here as one parameter. And you can see the mass stays relatively the same if we go to different detector combinations. And this makes sense because it's a parameter intrinsic to the system. So if we use more detectors, it shouldn't change much. However, there are other parameters, for example, the distance or especially the sky position, which of course change a lot if you include an additional detector. So, and I think the sky position is the most interesting. So if you just take one detector, here Hanford, basically you can't say anything. The signal could have come from any direction. If you then include the second detector here in gray, you can see it kind of gets restricted to this donut shape, which is already a way smaller sky region. And if you then include the third detector, you can really narrow it down and pinpoint it very precisely. Then, I just want to mention that we have fast inference, which means we can do the initial sampling within 10 seconds, and the important sampling can take around 5 to 10 minutes. But this is very important for the physicists because this means we can do a lot of events. So we can go crazy and say, okay, we take these 50 events, you analyze any detector combinations, you don't have to look at the details. And this is like 260 separate analyses. And with a standard approach, this would have been 250,000 CPU hours. And with our model, we can just do it within around 50. And the main cost here is the important sampling. And this is something which is really exciting for the physicists because we can actually speed it up quite a bit. Another thing you can do with this flexible model, is to test whether Einstein is wrong. And in physics, that's called testing general relativity. And what we do here is, okay, we observe two black holes merging into one final black hole. And we can now say, okay, this, for example, the mass of this final black hole, it should be independent which part of the signal we take. So we can take the inspiral part of the signal and look what the posterior is, what the mass is based on this inspiral part. We can also take the merger ring-down part of the signal and look at, does this produce the same mass? And ideally, so we now extract the final mass and spin based on both signal parts, and ideally they should be the same. However, if they're not the same, so here we now plot the difference. So the difference between the final mass and final spin here, if they're not the same, then of course this would show a deviation from Einstein's theory of general relativity. And then in our results we obtained, everything is quite consistent here with 0, 0, so there's not so much deviation. However, ideally at one point, hopefully, physicists hope that at one point we will find an event where there's significant deviation, and this will, of course, give us new exciting physics. So unfortunately, so far Einstein is right, but we can also now, I just want to say we can do these tests now quite quickly. So writing a paper can be easy, but actually making it a pipeline that physicists want to use is a different story. And before I finish, I just want to comment on this. So one goal we had is to integrate our framework into the physics collaboration. And this, of course, has different requirements. First of all, it has to be easy to use, it has to be well integrated. So, of course, parameter estimation is only one part in the whole production pipeline. So when the data comes in, we actually have to first calibrate the noise, you have to calibrate the signal, then you have to actually do the detection. So is there a signal at the moment in the detector or not? And then collect additional parameters, and then you do parameter estimation. And then based on these mass values and sky position values, there are downstream analysis which are done, for example, testing general relativity, but also looking at the population. So how do the masses look like of all events combined? Stuff like this on these results. And it has to be trustworthy and highly accurate. Only a small change in the posterior distribution, you have to understand where this actually comes from. So this means in the collaboration, what is happening is you say, okay, I want to use this code in a collaboration, and then you have to do an extensive code review where a lot of different sampler tests are performed. You have to show that your results are exactly the same as the standard methods results. And you also have to, of course, show that your model was well trained. And we actually now managed to have DINGO used in official analyses. So far, it will not be part of the official data release, but it has been run on current events that we're analyzing. So the takeaways from this talk I hope you took away that gravitational wave science is very exciting. There's a lot going to happen in the next 5 to 10 years. I'm looking very much forward to it. And with the work that I've done, we can now analyze a lot of events with different settings and check if Einstein is correct. And I prepared like the models uploaded to Zenodo, and there's a tutorial online which you can run and then, for example, reproduce the plot here on the right. So this is not only my work, we're a whole group working on this code base. And with this, I want to end the talk, and let me know if you have any questions or comments.
Hello. Part of what the neural network learns is basically denoising.
Yes.
Can you actually record noise data that is perfectly the same distribution? And also, wouldn't it be possible to kind of engineer a noise filter better? Like you can probably collect 1 million samples or something like that instead of using machine learning for that?
Yeah, so there are other people who are working on denoising. And one thing I did not comment on is that there are noise artifacts which are not consistent with this Gaussian noise assumption that we make. So we call them glitches. And they can come from very random sources like earthquakes, irregular noise artifacts of the laser. And there are like other people working on actually removing these noise artifacts to make the analyses easier. So that's also a very interesting thing. Yeah. I think here's a question.
So I have multiple, but I'll start with one. So you said you generate your noise curves, right? So and you have to generate them over and over again because you detect changes over time. So now you're not in a clean environment, right? You don't know, you can't separate the detector from the gravitational wave. So how do you actually produce the noise curves?
So do you, like, we kind of, when I say we generate the noise curves, what we do is we actually take measured data. So we take a stretch of the signal from the detector where there was no, a stretch of the data where there was no signal in it. And this is then an estimate of the noise. This is what you mean?
That's exactly what I mean.
Yeah.
So what I mean is, how do you know there is no signal? Because the signal can also be tiny.
The
right?
noise and not observed. Yeah.
Yeah.
That's a great question. So there's always, of course, so basically that's a question of detection. So if you have this incoming data stream, when do you detect that there's a gravitational wave? And there's always some probability that you haven't found all gravitational waves. So basically, if you just let these search pipelines run on the data, you get a lot of triggers. Basically, for example, these 50 events, there might be 1,000 or more triggers, but then you have to put some threshold on like the false alarm rate of how likely it is. And usually we place a false alarm rate of like 1 per year. So to be very confident in that this is actually a gravitational wave. And there are sometimes specific events where it's a little bit debatable if this is not like some noise artifact in there. Some events can be retracted if further analysis or better modeling like basically tells you that this was some noise artifact. Yeah, so there's always some probability that you might take a stretch where there's a signal present, but of course, basically this also tells you about like the noise background. Maybe that's not a signal you're basically not interested in at this point. There can be, because people are also thinking about a lot of different types of gravitational waves, not two black holes merging, but a supernova exploding, which would also produce a gravitational wave. And this is of course difficult to model at this point. And when the detectors in the future, the detectors will improve. There's also the space-based gravitational wave detector, which will be built called LISA. And of course, if you go to space, like you don't have noise. You have completely different like observation possibilities that will be super exciting. And there we don't know what we're gonna observe. Probably there will be a lot of gravitational waves overlapping. Like we will not be able to look at individual events, but we will have a whole background basically. Yeah.
Yeah.
Hi.
Sorry, it's again about noise, but like, so you have like 3 places where you like measure, right? So, can you like pinpoint from the noise like profile back onto like the 3 places where you like measure?
Yes.
Because that's like, I mean, for me, it's like if you like run in production, for example, you typically can do that, right?
So there are a lot of sensors placed around the specific sites, and this is very, very interesting. So one story about that, for example, is that at one point in, I think 2016, they had like very real noise artifacts in the detector, and then they looked at all like cameras and sensors, audio sensors all around the detector, and they're like, where does this come from? You can correlate actually, and some of these correlations you can reduce. And one very funny thing is that actually at one point they found that actually the sound that was reappearing at very weird intervals again and again actually came from a pipe, a cooling pipe, and one of the detectors built in the desert. So what was happening is that water was condensing on a cooling pipe, forming ice, and very smart ravens came and started picking on the ice to actually, like, it fell down, of course it melted and they had water. But we saw that in our detector. It's called the raven glitch. And now what they did, they isolated the cooling pipe, but very unfortunate for the ravens. But yeah, stuff like this, if you find out what it is, you can actually like counteract it, or you can calibrate the noise by actually like dividing out these artifacts that you can have from some other channels. So I think they have like around 300 separate channels that then they can try to correlate with the signal to see whether it's a noise artifact. Yeah.
Yeah, thank you. So one question, can you say anything about the simulators of the like you use? Because I guess simulations in GR are not that simple in general. And because you assume certain events, like you assume the black holes colliding or the neutron stars colliding, what other events could generate signals that you cannot simulate at this moment? Because that kind of prevents you from being able to see them in general. And a bit of a sci-fi thing, I don't know. If there is a wormhole, something like that, would that produce any gravitational wave? And could you detect something crazy like that?
Okay, great question. Let's start with the wormhole. It's exciting, I guess. So I think I don't know enough about wormholes to tell you whether this can produce a gravitational wave. But there are sometimes, there was one kind of weird event we call, like, gravitational wave events have a number. Like, it's a 6-digit number. The first 2 letters are the year, then the second 2 letters are the month, and the last 2 are the day. And for example, the first one which was detected was 150914, so 2015 in September the 14th it was detected. And there was one event, 231123, which looked very weird. Like, people used different waveform models to analyze it, and they got different masses, different like parameters actually. And to this date, it's not clear why. It could be a wormhole. I think there was a paper who said maybe it's some like more, I don't know, I don't want to say something wrong, but more like some more exotic thing. There were actually papers claiming that this might be that. What also was a claim for this event that it might be lensed. So what you can have is similar to basically if you have a very massive object in front, and light comes from the back, you can get these Einstein rings. You might have seen that. So the light gets distorted by this very massive dark matter in front. And the same happens for gravitational waves. They are also influenced by these heavy potential, like this very strong gravitational potentials. And this is called lensing. And people were also claiming maybe this event is actually lensed. So we don't know what's going on with that. Could be a wormhole. Yeah. Yes. 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 Yeah. So it depends. As I said, there's like this whole like basically spectrum of simulators, and on each stage people are working on it actively. So in my group in Potsdam at the Max Planck Institute for Gravitational Wave Physics, they actually built these simulators, and there's some people who built who basically build some more the faster simulators. What they do is they basically say, okay, that's the general shape of a gravitational wave, and then they use this very expensive numerical relativity simulation to fit certain parameters. And this is then basically more an analytic model, which is not physically not super precise, but it's fast. So you can then do a lot of analyses with this one. Then there's some more expensive models where you model the system of 2 masses as an effect of one body. And you model the whole in spiral, and then you project these changes in the space-time onto a long distance, right? Because we will sit very far from this merger, actually. And this is more complicated, so this maybe takes longer to simulate. And then, of course, people work on including additional physics effects. So one interesting thing is like, of course, if the two black holes in spiral, what I showed before in the beginning, is like both were roughly on a circle, moving on a circle. But of course, it could be a very eccentric orbit, like not circle-like, but very distorted, on which the two black holes move and spiral inwards. And this gives, if you observe an eccentric merger, this gives you information about how did these black holes actually meet. Because if the two black holes get created in the same galaxy, and then they merge, they will be on roughly circular orbits. But if basically two separate galaxies merge and the two black holes then finally collapse into one, then this means they come from separate galaxies. And then the orbit will be very distorted. And like maybe like if we actually are very sure about an eccentric merger at one point, this might be a Nobel Prize. Because it can help you a lot with constraining where the black holes form and how they actually then meet and merge and send out a gravitational wave. Yes, and then you can work on including such effects as eccentricity in your waveform models, or you can actually make these like numerical relativity simulations faster, which is also very exciting. Yeah. Yes.
I had a question about the like usage of this. So I assume, or I think I've understood that now, like one could build a pipeline. Like tomorrow there's a new detection. 15 minutes later, you have like a parameter estimation.
Yeah.
What does this actually like do? Like what does that help somebody, or what do people do with the fast inference then?
Yeah. What do they do? That's a great question. So there are different stages. So let's say the detector is running, like we're in October, 6 months from now, we've started the detector again. And then there's a detection pipeline which says trigger. We have an event. And then we start very fast initial analyses, and the main interest here is the sky position, because there are multiple cases where in addition to the gravitational wave we can observe light. One case is binary neutron stars, and as I said in 2017 this was a huge effort. All telescopes basically tried to observe the follow-up on the southern hemisphere. It was a very big collaborative project. So if this is going to happen again, everyone will be very excited. So basically the goal is to produce these sky maps very fast, within seconds ideally. Because in 2017, when they observed basically it took 2 weeks to actually then find, oh, there was a gravitational wave of two binary neutron stars. Then they sent out the alert, and then basically you didn't observe the merger from the light. You only observed it 2 weeks later, and this kilonova, how it's called, this lasted for a whole month. And so you were observing this, like the gravitational wave signal was very short, maybe a few minutes, but then this electromagnetic follow-up took a whole month, and they were able to observe it for the whole time. But the start, when they started observing it, was quite late actually. So the hope is the next time two binary neutron stars will merge, we will be early, and we will see way more physics because we can actually see what is happening right after the merger. So that's one thing. Another point, is if you have two black holes which merge in a galaxy where there's matter around them, then when they merge, this process can also kind of ignite the matter around the merger and then also send out an electromagnetic signal. This can be part of an accretion disk, for example. And this is why also we want to sky map fast. Even if black holes merge, you could say, oh, black holes, they are black, we're not gonna see anything. But in specific situations, we could actually, and they have been, basically there are some light-based telescopes who regularly follow up on these very fast sky maps. So these, I think, are the mainly interesting part. And another thing is, of course, if you then have this parameter space, there can be, I think by now, gravitational wave physicists are mainly looking at the interesting events, the outliers, the stuff which doesn't make sense. And if there's a regular two black holes merging, like we're not really caring at this point, unfortunately. But so if there's one of these special events comes in, then you want to follow up with different waveform models. You want to do additional analyses. So that's also really cool if you then have a fast result. Yeah.
And why is the electromagnetic response slower, or is it just that the event itself is long and then you want to start filming as soon as possible, basically?
Yeah, the reason is, of course, both gravitational waves and light move at the speed of light, so they will be like approximately equally fast. The problem is that gravitational waves, like the advantage of gravitational waves, is they move through matter, so they will arrive on Earth without any interference. However, light can be like reflected, like if there's some stellar matter in between, like a dust cloud or something, this will delay it. And additionally, for especially binary neutron stars, when these two binary neutron stars collide, it's a very violent process. So what's happening in there, we don't know yet, but the assumption is that you get, of course, new elements get created, it's a lot of pressure, stuff flies out in different directions, and then, of course, this is a lot of mass, so the matter will not, like, some matter will get ejected, but other matter will basically recollapse into it, and that's why it kind of takes quite some time until this whole system settles back to like a regular state of maybe a small black hole or maybe like again a neutron star. Yeah.
I'm gonna take one or two more questions. Was there a question here, I think, earlier? No? So there was one here and then a new one. Sorry, you already had, you can, yeah.
Hi. I was curious, what are like major problems about DINGO? So what is the community telling you why they are maybe reluctant to use it or hesitant? Because it sounds amazing and we've heard a lot of great things about it tonight.
Thank you. There are multiple things, right? Of course, it depends a little bit on the physics field, how much machine learning has been used in the past. And one thing which can happen is, or which has happened, which we're kind of still trying to like convince people otherwise, is that people before us, for example, have claimed they can get super fast, super good results, and they did not deliver. So basically, there were examples where people claimed they could do a lot, and then people were excited in the collaboration to actually use it. And then they were very disappointed to find out that it wasn't as good, as accurate, and as trustworthy as they had hoped. And then there are some people who, because of such incidents, then really are negatively, like, have a negative perspective on using machine learning. And then, of course, you have to do a lot of like investment in like trying to convince these people to use it. So I think this is one thing where you have to be very careful about what you state, what you can do. And of course, we really have to avoid it. And of course, the other physics field, for example, particle physics, where machine learning is used on a regular basis, because this field has used machine learning since the 60s, basically, or 80s. And in gravitational waves, since the field is kind of currently starting, it's like 10 years old at this point of like, since we do the data analysis, it will take some more time. I think people now are like using it and applying it to different kinds of stuff, which is really amazing, and adopting it for different problems. Yeah, and of course, then there are a lot of other problems which we ideally could solve with something like DINGO, which standard methods cannot do. And I think this is something that physicists tell us, you should do this, you should do this, you should do this. And for example, one thing is to train on real noise. So currently we have one noise realization, and then we still make this Gaussian noise assumption. And of course, if we then have some glitch in a detector, like a raven picking, then we cannot do the analysis. We get 0% sampling efficiency, and we cannot analyze the event. And this means we can tell that we are wrong, which is great, but on the other hand, we are not as robust as some standard methods. So we still have a lot of work to do this step beyond what we're currently doing. Yes.
Hey, I had a couple of questions about the tokenization.
Yeah.
So is it correct that the tokens right now are like pieces of the signal in frequency space?
Yes.
So two questions I had was, what role does the summary token play, and how do you calculate that? And also, can you remind me what you said about why you couldn't do this in time space?
Mm-hmm. Yeah, great questions. So first about the summary token. So this like inspired by some language processing and video image processing, where you say, okay, you have these tokens based on your data, just like data tokens, I would call them. And then if you want to summarize information from these tokens, of course, if you don't have an additional space where to store information, the model needs to encode it on top of the data information. And by using a summary token that's randomly initialized at the beginning of training, so it doesn't know anything, and you, of course, since you just use this then for your downstream part, the gradients will flow through it. So this means that you kind of try to summarize information in this, and you can kind of plot attention maps and see which part of the signal or which, like at which layer of the transformer information flows into the summary token. So it kind of is the place where we gather the information, which, because the parameters, they're different space, right? My data is maybe 100,000 data points, but my parameters are 15, so it's a different space. So it doesn't really make sense to include it, like encode it in top of the data, basically. Of course, you could also just take these data tokens and then pool without having the summary token, yeah. Yeah, and then for the second question, that was, can you remind me?
It is. Why did we have to do this in frequencies?
Yes. Yeah. So ideally, we would want to do it in both time and frequency. The challenge with time domain is that the signals look more complicated. So usually you will have a lot of oscillation going on, which is like a lot of unnecessary variation because it just corresponds to specific frequency values. So the signal looks easier in frequency domain. And that's why the standard data analysis in gravitational waves is usually done in frequency domain. People now start to move away from it. So because in time domain, for example, this cut that I applied, right, for the ring down merger part and the inspiral part, that's not very precise in frequency domain. Ideally, you would do it in time domain to isolate the ring down. But yeah, so people want to do it in time domain. People have tried. It's more challenging. And what we are trying now is to actually use time frequency domain. This is similar to audio data. It's basically a spectrogram, and then use vision transformers on this. And of course, this has advantages and disadvantages. You maybe have more tokens. You might, on the other hand, you might be able to isolate noise artifacts better. But it's still open whether we get the same accuracy compared to frequency domain if we go to time frequency. Yeah. Great, thank you all.
Amazing, thank you so much, Annalena.
Yeah, thank you for your questions.
Now we have a lot of pizza that arrived, so also let Anna have some pizza and then grab her for more questions. So thank you so much for joining us. Also, we have Alex and Word here from Dunia, if you want to chat to them. Then we have Nasim from Tip3 Systems, and then me and Rancha from our team. Have pizza, enjoy, and yeah, go mingle on gravitational waves.
Great. Thank you all for coming.
So good. We